In this chapter we're going to be expanding on the basic rules of probability that we've already talked about and be looking at some more general rules of probability. We're going to be looking at independent events, conditional probability, and along with conditional probability we'll be looking at joint and marginal probability as well. We'll be talking about the multiplication rule, using tree diagrams to organize information to help us determine probabilities, and then looking at diagnostic testing. To get started, let's go ahead and look at independent events. Two events are independent if knowing that one event is true or has happened does not change the probability of the other event. Now, as a quick side note here, please remember that this is completely different from the idea of events that are disjoint. So this is completely different than disjoint events. Now, another name for disjoint events, of course, was mutually exclusive events. So when we talk about disjoint or mutually exclusive events, remember that Venn diagram idea about two events that do not intersect in terms of their circle values in a Venn diagram. So again, completely different than disjoint events. Let's go ahead and look at some examples of some potential events here that could or could not be independent. First of all, gender and eye color, we don't see a prevalence or a relationship between a gender and a person's eye color, so they're independent events. An example that we could look at that's not independent is gender and height. Males tend to be taller, so there does seem to be a relationship between gender and height. We could talk about gender and level of cholesterol, and that one's not so obvious. You might think that men tend to have higher cholesterol levels, but we'd have to look at some numbers to determine that. It's probably independent, but I'm not sure about that one. And then we could talk about a person coming in to donate blood. One person's blood type is independent of another, of course, if they're not related. So those are the idea of independence. And again, independent is completely different than disjoint events. Now, this idea of independence comes into play when we're talking about different types of sampling. The two types of sampling we can have are sampling with replacement and sampling without replacement. Let's go ahead and talk about sampling without replacement. So when we talk about sampling without replacement, basically means you would pick one individual from your population and you don't put it back, and then you pick another individual from the population. Now, with small populations, this can have a big influence. For huge populations, it has very little influence. So let's go ahead and look at a specific example here. So for our first example, let's go ahead and look at a very small population. So we have a classroom, let's say, with 10 male and 10 female students. Now, it's pretty easy to see here for this example, the probability if we randomly select one person that the first student selected is a male would be 10 out of 20, which of course is 0.5, or about 50%. Now, we are going to sample without replacement. Now, this means that that person that was just randomly selected doesn't get their name put back in the hat to be selected. Now, if the first student is male, then the probability that the second student is male, we'd have to think about that one. There's only 9 males left to choose from because one has already been selected and not returned to the population. And since there's only 9 males left, I also have to think that the overall population has been diminished by 1, so my denominator here is 19. Now, in this particular case, 9 divided by 19 is about 0.47. And note that this is not equal to 0.5 that we had with our previous calculation. So again, it says pick one subject from a population and don't put it back, then pick another subject. So we definitely have sampling without replacement here. And we can notice that our picks are not independent. And pretty soon we'll learn some notation that helps us kind of summarize this in a little bit faster way. But our picks are not independent because what happened? The probabilities changed. Okay, so for a very small population, sampling without replacement basically leads to events that are not independent because one influences the other. The probability changes. Now let's go ahead and look at another example where we have a much larger population. So let's go ahead and look at the entire United States. And we're going to assume we have about 300 million people in the United States. And let's say half of those are male and half of those are female. And of course we know from our previous that that's not exactly true. That's off by a bit, but we'll assume it's a 50-50 split. Okay, so for this example, we're going to do the exact same thing. Let's go ahead and look at the probability that the first person, instead of student in this case, person selected is male. Well, that would be 150 million out of 300 million, which we can see is 0.5. And again, I'm going to sample my next without replacement. So if the first person is male, what's the probability that the second is male? Okay, well, our denominator is going to change slightly. Instead of being 300 million, it's going to be 299,999,999, because that first male that I selected will not go back into the population. Now, there's no longer 150 million males. There's 999,999. So 149,999,999. Now let's go ahead and look at the approximate probability of that when we divide it out. And this is equal to pretty much 0.5. And if you want to get exact, it's 0.49, repeating forever. But you can see that there's not much of a change here between these two probabilities. They're very similar, and this is approximately 0.5. So these are very similar. Now in this particular case, because my population I was selecting from, successive picks are nearly independent. And this is an important distinction. Now usually when we talk about events, they're either independent or not, but in this particular case when we talk about sampling without replacement, we can see that there's very little change in that probability when we have a very large population when we're sampling without replacement. So there's really very little effect that we're looking at there. Now I would like to be able to take this example and rewrite it using some probability notation. So let's go ahead and look at some probability notation, and we're going to start with the idea of conditional probability. Now when we talk about conditional probability, what we're doing is we're taking our entire population and we're narrowing it down based on a particular condition. So I could take I could take the entire population of the United States and I can condition it on students who are in college. And so that takes 300 million people in the United States, and it says let's only consider those who are in college right now. So conditional probabilities reflect how the probability in an event can be different if we know that some other event has occurred or some other event is true. So for the example that we just looked at with students, or with the entire population and then students in a class of 20 being split up, in this particular case with the smaller group, it did change. Our probabilities did change. In the larger group, the probabilities remained essentially the same. So let's go ahead and talk about conditional probability. Well, first of all, when we write conditional probability, we typically write it as the probability of, let's say, B given A. So this means the probability that event B occurs given, and this is a vertical bar, it's not a fraction bar, given that event A has already occurred. Now, we have a little formula that we can use for this. So this is called a conditional probability. This is equal to the probability of B and A. Have to get used to that, writing that out. B and A all over the probability of event A. So each of these has some different terminologies associated with it. So this is conditional probability. The numerator is joint probability, and the denominator is marginal probability. And so when you see this written out, sometimes you'll just hear it referred to as conditional, joint, marginal, and rewritten that way. So another way that we can think about this is conditional, C, is equal to the joint probability divided by the marginal probability. Now notice that this marginal probability that's in the denominator is always related to whatever the condition is, because I'm taking my population and I'm narrowing it down, so that becomes my new denominator. Another quick thing to note here, the probability of event A cannot equal 0 because I can't divide by 0. I would have an undefined fraction. A couple other things to note. B given A does not always equal A given B. In fact, it seldom does. This is not equal. Order matters how you write a conditional statement. Another interesting fact, probability of B and A, our joint probability, it doesn't matter how we write that one. So the probability of A and B is equal to the probability of its converse. So again, order matters for a conditional probability. Order does not matter for a joint probability. So the way we usually read this statement is we say the conditional probability of event A given, and again this is a vertical bar, event A has occurred is the joint probability of A and B, or B and A, divided by the margin of the condition. So that's how we would usually think about that. Now, when we have two events that are independent, this formula kind of changes a little bit. So if two events are independent, what ends up happening is the probability of B given A is just equal to the probability of B. And what this is saying is the fact that A has occurred has no influence whatsoever on whether B has occurred. So no information is gained from the knowledge of event A. And that's important here. So for independent events, the probability of B given A is just the probability of B. This is a great little test question, fill in the blank, so you might want to make a little note there. Now in our particular case, what we had up above for our examples, for our first example, when we had 20 students in the classroom and 10 were male and 10 were female, what we were looking at there was conditional probabilities. So the probability that the second selection was male given the first was male, that was our 9 out of 19, which was approximately equal to 0.47. So this is our shorthand notation of this. Now for our other example, when we had the entire population of the U.S. and we had 300 million people that we considered, and then we split it off into 150 million male and 150 million female, the probability that the second person selected was a male given the first was a male really had no influence or no effect here. It was still about 50% or half. So let's go ahead and go back to another example that we looked at in a previous chapter. These were when we were talking about Dalmatians. And with the Dalmatians, we looked at two characteristics. We looked at whether or not they were hearing impaired and whether or not they had blue eyes. So if you recall the Venn diagram that we had for our Dalmatian events, we had hearing impaired and whether or not they were blue-eyed. The and here, about 5% were both, so this is, I better make that look like a 0 instead of a 6. This is 0.05, and then we figured out these other probabilities as well. So let's go ahead and fill in the Venn diagram, and then we'll also fill out the rest of some probability statements. So the probability that they were hearing impaired and blue-eyed was 5%. Now the and is our intersection here, this middle wedge. We were also given that the probability that they were hearing impaired was 0.28. So that's why we have the 23 plus 5 is 28. We were also given the probability that they were blue-eyed was 11%, 0.11. So that's our 5 plus 6 is 11 here. Now if we add these up, the probability of H or B, we can follow that addition rule that we learned in the last chapter. That's the probability of H plus the probability of B minus the probability of H and B, because we counted that intersection twice. This would be 0.28 plus 0.11 minus 0.05. So if we look at this and we add all of these up, we get 0.34. Now this OR would be if I shaded in all of the circles, nothing on the outside. Now when I want to find out what's going on outside of these circles, I can take 1 minus the probability of H or B and I'd get 0.66 out here. So this probability, 0.66, is neither H nor B. So that'd be hearing impaired nor blue-eyed, and that's 0.66 for this particular case. So again, this is kind of a review of filling out a Venn diagram. Now let's take this information and let's try to extend it toward independence. So, are the traits H and B independent? So is there a relationship between whether a Dalmatian is hearing impaired or has blue eyes? That's what we're trying to figure out. Well, one way that we could check for this is we could try and determine some of the probabilities. So we could look at the probability of hearing impaired given blue-eyed and look to see, does this just equal the probability of being hearing impaired? If this is true, that would mean that the two variables are independent. Now as it turns out, I don't have to check both. I don't have to check both H given B and B given H. I can just check one. So let's go ahead and check it out. Let's look at the probability of H given B. From our formulas for joint, conditional, and marginal probability, conditional probability is equal to the joint divided by the marginal. So our joint probability, we know from up here, is 0.05. And my marginal probability, the probability of B, is 0.11. And if I divide those out, I get something that's approximately equal to 0.45. Now what we need to do is we need to compare this to the probability of H. So we've figured out what this one equals. Now we need to go back to look to see what probability of H equals. So from up above, the probability of H from up here is 0.28. Now notice, these are not equal, and that's what we're trying to get at here. So what we have figured out is the probability of H given B does not equal the probability of H. Therefore, H and B are not independent. So hearing impaired and blue-eyed are not independent. There's a relationship between them mathematically. And maybe we can establish something like the higher proportion of hearing impaired dogs are blue-eyed. or vice versa. So again, we've established here that 0.45 does not equal 0.28. The conditional probability is just not equal to the probability of H here, so the events are not independent. And that's one way that we can work to establish whether events are independent or not, is going through that process. So this is a hugely important idea, is how do we determine whether events are independent. So it's important to know that process. The next thing we want to look at is the multiplication rule. Now for the multiplication rule, again, what we're trying to do is we're trying to talk about joint, conditional, and marginal probabilities and trying to relate them to each other. So for the multiplication rule, we start with something we already know. We start with the probability, let's say, of B given A. So the probability of B given A is the probability of A and B divided by the probability of A. We already know this. The conditional is equal to the joint divided by the margin of the condition. Remember, this is already related. Now what we do is we use some algebra and we solve for the joint probability. So we multiply both sides through by the probability of A, and we can see here that these will cancel, and what we have here is a new formula then. We have the probability of A and B is equal to the probability of B given A times the probability of A. So this is our general multiplication rule. And this is true for any two events. So let's go ahead and write that out. Now if we look at the probability that any two events, A and B, both occur, that's the probability of A and B, it's equal to the joint probability is equal to the marginal times the condition. And again, look at the relationship here. This will always be true. Now we have to be careful here. There's a couple other ways we can rewrite this. We could also rewrite this as the probability of A and B is the probability of B times the probability of A given B. So we could rewrite this. Remember, order doesn't matter when we rewrite a joint probability, but it does matter when we rewrite a conditional probability. So that's why this marginal has changed. So these are both true statements, different ways we can write this. Now this rule will change a little bit if we talk about independent events. If I have independent events, what ends up happening here is this conditional, the probability of B given A, it basically falls down into just the probability of B. Because if I have independent events, the probability of B given A is equal to just the probability of B for independent events. So what I'm doing is I am substituting in. I'm taking this value and I'm substituting in for just the probability of B. So these are my multiplication rules. This will work for anything because if I have independent events it breaks down. This rule only works for independent events, and these definitely are important and you should know when to use which one. The next thing we're going to look at is an example of using this idea of the multiplication rule. So for this example, we're going to be looking at this multiplication rule. So let's go ahead and go back to our pond idea again. Or not our pond, our classroom. Sorry, our classroom idea. So we had a classroom with 20 students. And 10 were male and 10 were female. Now we've already established that successive captures are not independent because we're sampling without replacement. Let's go ahead and determine the probability of randomly selecting two male students in a row. So the probability of randomly selecting two male students in a row. So another way that we could write this then is the probability that the first selection is male and the probability that the second selection is male. Well, one shouldn't influence the other if they're independent, but we've already established these are not independent because I am looking at this with sampling without replacement. And again, if you want to verify this, you can go back up and look in this same example that we just did. So for this example, I can't just multiply these together because I do not have independence. So this is a joint probability. A joint probability is going to be equal to the conditional times the marginal. Now my notation here is the probability that the second is male given the first is male times the probability the first is male. Now I could have also rewritten this as 1 given 2 times the probability of 2, but that would have been a lot more complicated. So let's go ahead and write this out. The probability that the second is male given that the first was male basically is that probability we've already found. It's 9 out of 19. Now the probability that the first was male was 10 out of 20. Now if we multiply these out, we get a probability that's about 0.237. So again, we've already figured this probability before, 9 out of 19. This is our conditional probability, and the probability that the first was male was 10 out of 20. So the probability that 2 randomly selected students in a row are male is about 24%. So that would be an example of how we can use this idea of events that are not independent and applying that multiplication rule that we just learned. Let's go ahead and look at another example where we're looking at blood type. Now we're going to be pulling in that blood type chart that we've used in previous examples to determine the probabilities of the blood type distributions. So for this example, we're going to have to remember that unrelated visitors are independent. So in our previous example, they were not independent events. In this example, they are independent. So keep that in mind. I would like to look at the probability that the next 2 unrelated visitors are both blood type O. So one way that we could look at this is the first visitor is O and the second visitor is O as well. Now because these are independent, I can just multiply the probability. First is O times the probability that the second is O. Well, from over here, when I want to look at the probability that they're O, blood type O, I would take the rhesus positive and the rhesus negative and add those two together. 38 plus 7 is 45, so this would be 0.45 times 0.45, which is about equal to 0.2025. So about 20.25% would be the probability that the next 2 unrelated visitors are both blood type O. And this was using the idea of independence to determine that. Next thing we're going to look at are tree diagrams, and basically tree diagrams can help us organize probability information, and then once we have that probability information organized, to determine more probabilities from the information. So let's go ahead and look at tree diagrams. John, would you try on your wrestling shoes this morning too? Make sure we don't need a extra pair. How about you, Jean? Are you doing okay? So for this information, or for this example, we're going to be looking at the relationship between gender and skin cancer location. So let's go ahead and look up some summary data first, and then we'll try and put it into a tree diagram. So in a randomly selected individual with skin cancer, let's go ahead and look at some values. So in a random individual with skin cancer, these are some locations and the probability of those locations. And this is skin cancer. So the probability that the skin cancer is on their head is 0.15. The probability that the skin cancer is on the trunk of their body is 0.41. And the probability that it's on their limbs is 0.44. Now, as a quick side note, we'd have 41 plus 45, 44 is 85, 85 plus 15 is 100%. So note that the sum here is 1, or 100%, and that's one thing that we should always be kind of looking for. Now let's go ahead and look at the percentage breakdown in each group who are women. So the percentage in each group who are women. Now we're going to have a lot of numbers running around here, and it gets kind of ugly, so that's why it's important to be able to take this information and either put it in a table or in a tree diagram. So the probability that we're looking at here is the probability that, given I know that the skin cancer is located on their head, what's the probability that that patient is a woman? That would be about 56%. I could also look at the probability that, given the skin cancer is located on the trunk of the body, the probability that it's a woman is about 37%. And then, given that I know the skin cancer location is on the limbs of the patient, what's the probability that that person is a woman is about 80%. Now, just as a quick side note, we can see here that these do not sum to 100%, and they shouldn't. What I can do is I can determine the probabilities here that will sum to 100. So each of these is a distribution within and of itself. So what we do is we condition on where the cancer is located, and then we run through all the different possibilities for gender. Well, if it's not a woman, it's a man. And the complement of 56%, or 0.56, is 0.44. Now note here that the sum is 1. Now this one, the condition remains the same, and then I run through all the possibilities for gender, which would be male in this case, and the complement of 37%, or 0.37, is 0.63. Now over here, again, condition stays the same. I run through all the possibilities for gender, and I'm back to male, and the complement of 80% is 20%. So notice in this particular direction, that's when my probabilities sum to 1. Each of these sum to 1. So each of these is their own little distribution. So from given information, I can determine all these probabilities here in purple. So I'm given some information to start with, and then I can work with these probabilities from here. Well, what I want to do is I want to take all this information and put it in a tree diagram to help us organize it. Okay, so let's go ahead and produce that tree diagram. Now the first branch of this tree diagram has to do with where the cancer was located, where the skin cancer was located. 15% of incidences were on the head, 41% on the trunk, 44% were on the limbs. And then what I do is I look at this and I say, okay, of those people who had skin cancer on their head, I'm going to split them up into male and female. Now notice this sum right here is 1. This sum right here is 1. This sums to 1, and so does this value right here. So what this is this is our conditional probabilities from up here. So here's our 44 and 56. And if we run right back up here, there's my 44 and 56. So what this statement is this is the probability, and I'm just going to do this first one. You can write them all out if you wish. This is the probability, and again this is our 44% from right up here. Probability of male, given I had skin cancer, location is on the head. So this is M given H. This probability would be woman given H. And then I could go through each of these, and each of these probabilities can be given. Now this is an interesting probability out here. This is the joint probability of man and skin cancer located on the head, because that would be the probability of M given H times the probability of H. So that would just be 0.15 times 0.44, which is equal to 0.066. And I can go through this for each of these. This would be woman and head. And again, this is the probability of woman given head times the probability of head. So this would be 0.15 again. But now the probability of woman in there, woman given head, is 0.56. And when we multiply that one out, the 0.15 times 0.56, we get 0.084. Now, if you notice, these are not summing to 1 right now. But as I go through and I determine each of these probabilities, these will actually show up and sum to 1. So I'm going to use T for trunk here. And here this would be a limb. And again, I keep using that and symbol. L for limb. And I can determine these probabilities. And again, they're all conditional. And so you can fill out the rest of the table. So go ahead and fill out the rest of that table. So when you get done filling this out, note down here that when I add these up, that these sum to 1. Now, you can also organize this information in something called a contingency table. And if you have any questions about a contingency table, let me know if the tree diagram's not working for you to determine probabilities. So from here, we have tons of probabilities running around. And we have a lot of different distributions. So again, it's important to keep track of what's marginal, what's conditional, and what's joint probability. Now we're going to take this information and we're going to be looking at diagnostic tests. Now we're not going to use this same data set again that we just did up above. We're going to be using a little bit different one. But the important thing to remember is some different terminologies here. First of all, we're going to be looking at the sensitivity of a test, the prevalence of a disease, the specificity of a diagnosis, and it's going to come into play with a tree diagram. So let's go ahead and pop that tree diagram up and then talk about the individual events that are in the tree diagram. Now a good idea would be to take a screenshot of this and put it into your notes, because there's a lot going on with this test, or with this tree diagram and these tests. So first of all, some terminologies that we want to look at are disease prevalence, the diagnosis sensitivity, the diagnosis specificity, and then also what these mean in terms of probability. So disease prevalence is basically how prevalent the disease, or the percentage of people in a population who have the disease. So to determine disease prevalence, we just take the number of individuals with a disease divided by the total number of individuals. So this is kind of our branch. So our first branch is we have an individual and they either have the disease or they don't have the disease. So that's our first branch. And then what we do is we go through and we give them some sort of a test to determine whether they have the disease or not. And of course, tests are not 100% accurate, and so from this result, after we give us this test value, we could get a positive or a negative result depending on whether the person has the disease or not. Well, at this point, this is saying diagnosis sensitivity is the probability that a person tests positive given I know they have the disease. Now if they have the disease and they test positive, this is a good result. Okay? Now, if they don't have the disease and they test negative, this is a good result as well. So these are the types of test results that we like to get. These test results are the ones we don't like. This basically means we have a false negative. they have the disease and the test says no, they don't have it. So we might delay treatment for the disease, so that would not be good. In this particular case, what happens is they don't have the disease, and what the test results said is that yes, they do have the disease. So we might start treatment on somebody who doesn't need treatment. And so we don't like the false negatives and we don't like the false positives. It's important to know the definition of false negative and false positive, so make sure you keep these in mind. Now the conditional statement here for diagnosis sensitivity is the probability of a positive test result given they actually have the disease. And this is a good result. Diagnosis specificity is talking about how we get that true negative, the probability of a negative test result given they do not have the disease. Now there's one other term here that I want to throw in the mix, and that's positive predictive value. Now positive predictive value refers to a conditional probability as well. If a person gets a positive result, what is the probability that that person actually has the disease? So that's the positive predictive value. Now this is not on this table up here. This would be if we work the table backward. So a positive predicted result means I know I have a test that's positive. What's the probability that they actually have the disease? And you'd think that it would be, you know, up here on this table somewhere, but remember the table works a little bit backwards. So this is a very informative piece of information when we can cull it from our data. So let's look at an example where we might be able to come up with that. The example that we're going to be looking at, we'll start with the idea of the prevalence of HIV/AIDS antibodies in a large population. So for this example, we're going to suppose that about 1% of a large population has HIV/AIDS antibodies, so they would be HIV positive. The enzyme immunoassay test has a sensitivity of 0.9985. Well, my sensitivity here, remember, is the probability, and again you can scroll up in your notes to have a look at this. This is a probability that I have a positive test result given that I know that this person has the disease. And then I also have a specificity here, and that's the probability that I get a negative test result given the person does not have the disease. So again, these are conditional probabilities. Sensitivity is a true positive. Specificity is basically our true negative. Now, when I'm looking at this particular example, what I'd like to do is to determine if this person tests positive, what's the probability that they actually have the HIV/AIDS antibody. So we're kind of looking at the PPV here, which if you recall from our previous notes was the positive predictive value of this test. So let's go ahead and throw out some tree diagrams again to try and help us determine what's going on here. So this is similar to the tree diagram that we just did, but we're filling this in with actual values. So disease incident would be 1 out of 100 have the HIV antibodies, which seems actually quite high, but it makes our numbers easier to work with here. 99% do not. Now this is our sensitivity. This is 0.9985 here. This is a probability that I know that they have the HIV antibodies, they have the disease. What's the probability of a positive test result? 0.9985. And then the complement of 0.9985 is 0.0015. So these sum to 1. And the same thing will happen here as the specificity comes into play here with our true negative, and these will sum to 1 as well. So I would think it's really important to get an idea on how to produce these tree diagrams. And so again, going back to this example will always be very helpful. So the question is that we want to answer is if a person who takes this test gets a positive test result, what is the probability that that patient actually has HIV/AIDS? So in terms of a probability statement, let's write that out. So this is actually the probability that we're looking at here. Now notice order matters when we're talking about a conditional statement, so I can't just switch this around and say, oh, I already know that information. Positive result from up here, given I know they have the disease, is 0.9985. That's not true. We have to actually go through and calculate this probability, and I think you're kind of going to be shocked a little bit at how high it is. So let's go ahead and look at that value, the PPV, which we can see from up here is the positive predictive value, and that's a probability that they have the disease given they tested positive. So let's look at the probability of HIV/AIDS given they tested positive. I'm going to try and abbreviate this a little bit. Well, that would be the probability that they have HIV/AIDS and tested positive divided by the probability that they tested positive. So what we're going to want to do is we're going to want to go through and calculate each one of these values. So the first thing that we can look at is the probability of a true positive. And that's this value right here. So the probability of a true positive is going to be equal to the probability of having the disease and testing positive. So this is basically taking this joint probability and rewriting it as a conditional. So this is the probability of positive given disease times the probability that they have the disease. And from this table we can see that the probability of positive given disease was 0.9985. The probability that they had the disease or the disease incidence was 0.01. So the probability here should be 0.00985. Okay, now the next thing we want to look at is the probability of a false positive. Now a false positive would occur if we have no disease and there's a positive test result. So this would be the probability of no disease given, or sorry, the probability of no disease times the probability of a positive test result given no disease. So I have my joint and my condition here. If I multiply these together, the probability of no disease is 0.99. The probability of positive given no disease we know from up above on our table. Probability given no disease is right here. So positive given no disease is 0.006. So I'm just multiplying that branch together. So now when we multiply these probabilities, what will we get? So here that ends up being 0.00594. So 0.00594. Now what I want to do is to determine that probability. And again, the PPV up here stands for positive predictive value. So that's what I'm looking for. So the positive predictive value of the test is the probability that they actually have the disease given they tested positive. So I take everyone who tested positive and put them in one room, and out of all those people who are in that room that tested positive, I want to figure out what's the probability they actually have the disease. This is the probability of disease and positive. Conditional equals joint divided by the marginal, and this is the probability of positive test result. So disease and positive was the probability of a true positive, and so that was your 0.00985, and the probability of being positive is actually made up of two things. It's made up of the true positive and the false positive. So that would be 0.00985 plus 0.00594. And if I divide these out, I will actually get a value that to me is quite shocking. You get a value of 0.624, or about 62.4%. So this test doesn't seem all that good. Out of all the people who tested positive, only about 62.4% of them actually have the disease. So that test from that direction, the PPV, and again the PPV stands for positive predictive value of the test, it's not so good. You'd think it would be a little bit higher. Okay, so let's go ahead and take this same information and organize it in a contingency table. It's just another way to look at it. So a contingency table talks about joint probabilities here and marginal on the outside, and then I can find conditional probabilities. So I have test result could be positive or negative. The disease result could be I actually have the disease or I don't. This means the complement, not disease. Okay? So from my table up here, I have a couple of pieces of information. I have this false positive. Well, the false positive down here is this joint probability, and the false positive means no disease, and I test positive for the result. So I get 0, 0, 5, 9, 4. So this is no disease and a positive result. And then from up above, we know the disease and positive is 0.00985. And then to fill in the rest of the table, I actually just add the columns and rows. And so to find the probability of a positive result, I would just add across. So 0.00985 plus 0.00594, I get 0.1579. And then to find this value, I can subtract from 1, and I get 0.98421. That tells me that these two numbers here better add to 0.98421. I can find out my value here if I take 0.01 minus 0.00985, and I get 0.00015. 0.99 minus 0.00594, 98406, and then I'm just going to double check this number across by adding those, and I do get that 0.98421. So from this contingency table, finding the PPV is pretty easy. The probability of disease given a positive result, I just look across from positive and I say, okay, I'm going to take all of the people here and just limit it to 0.01579 for my denominator, and then out of these values, how many actually have the disease? So that would be my 0.00985. So to find this conditional probability, I just use this row and I condition on this row, and I'm just looking at the probability of these events. Now if you divide those out, you have your 0.00985 divided by 0.01579. I get the exact same value I do up here. I get that 0.624, about 62.4%. So I like a contingency table. To me, it's a little bit easier to keep track of, but you still have to find these probabilities on the inside. And it doesn't matter to me whether you use a contingency table or a tree diagram to keep track of these, but the important part is do something to keep track, because there's a lot of data running around. There's a lot of information, and you do need to have some way to keep track of it, so you can use ideas like the complement to find conditional, joint, and marginal probabilities. These take some practice. Don't get frustrated when you're working with them. Try and organize the data in a contingency table or in a tree diagram.